All right. All right. So we have discussed hypothesis testing. We have discussed about all the different types of hypothesis testing: one sample, two sample, and more than two sample. Now we will talk about some other advanced topics of in statistics known as correlation and regression. So let's understand what correlation is, and then we will talk about regression. So before we get into correlation, anybody has any questions or anything? Okay, so what is correlation? Correlation is a statistical measure to understand how the variables are correlated to each other. Now, where the correlation is required. Um, so we have seen right through statistical test, we are checking whether how the variables are impacting the other variable, right? Whether the variables are significant or not. So that's something we are checking through the through those hypothesis testing. So where ANOVA will tell us whether one continuous variable is correlated to a categorical column or not. So if we have four categories, then we will have four different samples, uh, measuring these continuous variable. So yesterday we have seen the example like the impact of the teaching methodology on the value. So here the value was a continuous variable and the teaching methodology is my categorical variable. So if we want to understand if these two variables are related to each other, we can go with an ANOVA. Chi-square test is about finding out the relation or um, the basically impact of the one categorical variable on the other categorical variable. We have seen that how the uh, income group is impacting other categorical variable through the chi-square test. So the continuous versus categorical, you can do it through ANOVA. Categorical versus categorical, you can do through chi-square test. Now, correlation will help you to find out the relationship between continuous and continuous variable. So, for example, if you want to find out how the price is impacting your sales, okay, how the temperature is impacting the voltage. So here, how the height is impacting the weight, right? So all these two variables are continuous. So for that, we go and use this correlation. So for correlation, we have multiple measures to understand how these are related to each other. One is like covariance, another is correlation coefficients. Let's understand the covariance. We know about the variance. What is variance? So variance is calculated for one single column. Okay, if we have one continuous column, let's suppose X, and we have X1, X2, X3, X4 in one single variable. So the variance formula is sum of squared of the deviations of each of these values with the mean xi minus x bar whole square divided by n minus 1 when we are talking about sample. So now the covariance is all about finding out the relationship between the two continuous variables. Let's suppose x and y. Now you have x1, x2, xn. Now you have y1, y2, yn. You can consider this x as price and y as sales. So how this price is impacting your sales, you can able to understand through this covariance. Now the formula of this covariance is it is denoted as co x comma y. It is I equal to 1 to n xi, you will find out the deviation of each of the values with the mean of that particular variable and multiply that with the deviation of the other variable divided by n minus 1. Now, this is your covariance. You can denote it as sum of squared between x and y and divided by degrees of freedom. Okay. So this is my covariance. As the name suggests, covariance, how the variance is changing with respect to other variable. That's something we will identify through this covariance. Now, it will give you the values between, minus infinity to plus infinity. If the negative value you will get, that means these two variables are inversely proportional. If you get the negative value of covariance, in that case, your y is inversely proportional of x. If it is negative, if it is positive, then y is directly proportional of x. If there is a change in x variable, 1 unit increase in the value of x, then there would be an increase in the value of y. If that's the case, then the covariance will come out to be positive. If there is a increase in the x value, but there is a decrease of y value, then it is considered as a inversely related. Okay, there the covariance would be negative. So, for example, sales and price. We see that if the price is reduced, my sales would increase. You will get more demand of that particular product, right? People will buy more those products, which gets cheaper, right? So, in this case, those are inversely proportional. So, for example, height and weight. If your height is increasing, then your weight would increase. Okay. If your years of experience is increasing, your salary would increase. Then in that case, it is directly proportional. Through with this covariance, this measure, if you get the negative value, you can conclude that there is an inversely proportional. And if it is positive, then you can say it is a directly proportional. So whether it is a positively correlated or negatively correlated, that you can identify through this covariance. So basically, the direction of the relationship can be defined or can be identified through this covariance. But the strength of the relationship, how strong the relationship is between these two variables, that something cannot be defined through this covariance. For that, we use the correlation coefficient. So correlation coefficient formula is covariance. Sorry, we I. So I'll write it as COR of x and y is equal to covariance of x and y minus divided by standard deviation of x into standard deviation of y. Now this is the formula of correlation. Now if you use this correlation, then you will get the direction as well as the strength of the relationship, how strong the relation, both through this correlation coefficient. So in our analysis, majorly we go with the correlation coefficient because we get the direction as well as the strength of the relationship. Direction will tell whether the two variables are inversely proportional or directly proportional, and the strength will tell me, how strong the relationship is between the two variables. You can also define this SS covariance of x and y is SS xy by degrees of freedom. Okay, and this Sx or Sy, you can put it as SSx by degrees of freedom into SSy degrees of freedom, where degrees of freedom is equal to n minus 1, right? If you further simplify this degrees of freedom will get cancelled out. Then you will get SSxy by square root of SSx into SSy. Sum of squared of x and y, which is this, divided by SSx. SSx is square of the deviation from the mean. yi minus y power x square. So this is your SSX and this is your SSY. Okay. So this is how you can find out the correlation between the x and y. Now the unique feature of characteristics of this correlation is that this would range between -1 to +1, where in this case it was between minus infinity to plus infinity. So I cannot quantify how strong the relationship is, right? But here I can quantify how strong the relationship is because here the range of the values is between -1 to +1. If the values of the correlation is close to 1, so that means they are strongly positively correlated. If it is close toward -1, then I can say that they are negatively correlated. So if it is like zero point 0.9, so I can say they are very strongly negatively correlated. If it is towards +1, like plus zero point 0.9, then they are strongly positively correlated. If it is close to 0, that means the relationship is not strong. Okay. So there is no relationship. There's no relationship between the two variables. So I'll take a pause. Let me know if this is clear. Covariance and correlation. Is this clear, everyone?
Can you once again tell like the difference of covariance and correlation coefficient?
Okay, let me slide. So covariance of x and y is equal to 1 to n xi minus x bar yi minus y bar divided by n minus 1. Or else you can put it as ssxy by degrees of freedom. This is my covariance and it range between minus infinity to plus infinity. So if the values are positive towards positive, then those are known as positively correlated. If it is negative, then it is negatively correlated. Negatively correlated means the y is inversely proportional of x. Positively means y is directly proportional of x. So you will get only the direction of the relationship, how the variables are related to each other, that you can identify through covariance. When it comes to correlation coefficient, so we define it as COR xy. Now this is covariance of x and y divided by standard deviation, okay, of sigma x and sigma y. Or else you can put it as SSXY divided by SSX into SSY. Okay. Now this would range between -1 to +1. So infinity is like any number. You cannot quantify which number is higher, right? There is no limitation. Okay, so any positive value, any negative value, you can get it in covariance. But here there is certain range of the correlation. Your values, whatever you will get out of this particular equation, it will lie between -1 to +1. So if it is -1, then it is known as strongly correlated, negatively correlated. And if it is positive +1, then it is strongly positively correlated. Okay. Now, how this correlation would help us is basically if I have two variables, like input variables, x1 and x2. Now, I want to see that how each of these input variables are impacting my output variable, which is y. Then I will find out the correlation between each of these variables with y. So correlation of x1 with y and correlation of x2 with y. Now I'll compare these values. Based on the values, if let's suppose here it is 0.9, here it is 0.6, then I can say that this particular x1 is strongly correlated to y when compared to x2. So this kind of relative um, study or analysis I can do between the variables to check which of the variables are strongly correlated to my output variable or to any other variable. And here in this correlation and covariance, the two variables, whichever I'm talking about, or on which I'm going and calculating the covariance and correlation, has to be have to be continuous variables. Because this variance and all those things I cannot calculate on the categorical variable. So it is only used for two continuous variables. Okay. Now is it clear?
Yes.
Okay. So now that's about the correlation. Now let's understand about regression. So before getting into a regression, let's understand the need of regression. So see, correlation will give you the direction and strength of the relationship, right? That we have seen. So the values will come out to be one single value that would range between -1 to +1. So once you understand, yes, these two variables are related to each other, now you would be interested to know how they are related. Okay. And that relationship will be defined by regression analysis. Now, regression will tell you how these variables are related. Now, just think about an equation. Like if I'm saying y equal to 2.5 plus 6 times of x. Okay, let's suppose this is my equation. Okay, so earlier where I just got to know that, okay, these x and y are related to each other. Now with this regression analysis, I can able to define an equation which will tell me how they are related to each other. Okay, in what equation, they are related to each other. Now this regression, you see that you can compare this equation with the equation of straight line. Okay, so you know about the equation of straight line, it is mx plus c, right? So you can relate to this particular equation. Now this m is nothing but your slope and the c is nothing but your intercept. Okay. So for example, in a line, if this is a line, if this equation of this line is y equal to mx plus c, where y is your y-axis and x is your x-axis. Now this is defined, let's suppose this equation is defined by y equal to mx plus. Now this is known as intercept. Now, the slope is defined by 1 unit change of x. What is the change on y? That is known as slope. Slope is nothing but delta of y by delta of x. Okay. Now, this particular equation can be defined or can be identified with this regression analysis. Now, this particular equation, you can use it for your predictions. Now, this is known as regression modeling, where you build these regression models, okay, which will be in the form of equation. Now, this equation, you can use it for your prediction. Now, let's suppose at a particular x, you want to find out what would be the y. So you use this equation, substitute the values in this particular equation, and then you can able to calculate what is y. So for example, a small example, if I want to give, let's suppose this is my x and this is y. I'll say 2, 5, 3, 7, 4, 9, 5, 11. Suppose I'll give you these numbers, x and y. First, you go and check what is the correlation between x and y, and it will give me a positive value because if my x is increasing, my y is also increasing. So obviously, it is a inversely proportional, and my values would be positive, correlation positive. Depending on the value of the correlation, I can also understand how strong the relationship is, x and y. Okay, it will give out to be a very high number, 0.9 or something. Okay. Now, I am interested, to understand how they are related so that if I'm going with a number like 12, I want to know what would be my y. Okay. So these kind of questions you might have seen in the aptitude test for any competitive exam, you may see like these kind of questions may come up like They will give you this kind of thing and they will ask you to, okay, now tell me what would be the number here, okay, at y. So can anybody solve this question? Can anybody tell me what would be y? See, now your model is getting trained now, okay? You're training your model.
19.
19?
Yeah.
You sure? First, try to find out the relationship between x and y. And if you identify the relationship between x and y, now this would be simple for you to calculate. So you're saying 19. How many of you are saying 19? And this is a very, very simple problem. I'm saying if x is 2, y is 5. If x is 3, y is 7.
X1 plus X2 is Y1.
x1 plus.
X2
See,
is Y1.
you have to take it as an independent example. If my x is 2, my y is 5. If my x is 3, my y is 7. Now you define the equation, something like this, okay, with these numbers. It's a very simple number, guys. See, 2 into 2 plus 1, 5. 3 into 2 plus 1, 7. 4 into 2 plus 1, 9. 5 into 2 plus 1, 11, right? So can I say that y is equal to 2 times of x plus 1, right? Now you substitute this x values and this y will exactly, you can calculate by this equation. So 2 into 2 plus 1, 5. 3 into 2 plus 1, 7. 4 into 2 plus 1, 9. 5 into 2 plus 1, 11, right? Now, if you have 12, now what you do is you will just go and substitute that in this equation. 2 into 12 plus 1, which will equal to 25. So now 25 is the answer. Now, if I give you any x value, for example, I give you 234 as x, you can easily able to calculate y by just substituting the values for this. Now, this will act as my predictive model. Now I can predict y based on the x through this regression model. Now, if you see that this regression model is only capable of giving you a linear equation. So these are also known as linear models. It can able to give you a equation of a linear line, straight line. So that's the reason it comes under a linear model family. Okay, so it will generate an equation which will give you a line of equation of a straight line. Okay, now this is known as a regression analysis. Regression analysis, in short, it will quantify, it will tell you how the variables are related to each other. It will tell you how, while correlation will tell you in what direction and what is the strength of the relationship. Okay, now let's talk about linear regression in detail. Now, this regression analysis is called as linear regression because it gives you a linear equation. Now, it has two types. One is simple linear regression, another is multiple linear regression. And there are some advanced concept like, you will find out the polynomial linear regression. Okay. But this is out of course, we will discuss about simple and multiple linear regression. So what is the simple linear regression is when you are considering one input variable only to predict your output variable. Output variable, target variable always needs to be one only. Okay, you will predict only one single variable at a time. So in any of your predictive analytics problem, there would be only one output variable. So to predict that particular output variable, if you are considering only one single variable, then it is known as simple linear regression. And again, here the output variable has to be continuous. But this input variable can be either continuous. In the simple linear regression, it has to be continuous. But when we are talking about multiple linear regression, it could be a combination of continuous as well as categorical. So here I will put it as only continuous as we are discussing about simple linear regression only. I'll not confuse you. So we will go with a correlation, and in correlation, we understand that we can find out the strength of the relationship and the direction of the relationship between the two continuous variables. And then we go and use this simple linear regression to understand how these two variables are related. And we will come up with a linear equation. Now that is known as simple linear regression. Okay. So for example, now this is the data, let's suppose, okay, I want to predict this continuous values. What I want to predict here, let's suppose I want to predict the CO2 emission. Sorry, I want to predict the CO2 emission. So now this will become my output variable. Now this Y in data science, a variable which you want to predict can be called by different names. It is called as dependent variable. It is called as output variable. It is called as target variable. It is called as response variable. There are multiple names given to it, this particular variable. Okay, so here we are calling it as a dependent variable. Now the input variable is called as independent variable. Now this particular Y variable is dependent on X. And now that's something, okay, we are going to define how they are dependent. So it is dependent or related with this particular kind of equation. Or else in statistics, we talk as beta 0 plus beta 1 X. Okay, so these beta 0 and beta 1, they are called as coefficients. Okay, and these coefficients we will calculate through the regression analysis to come up with this kind of equation. Here the input variables are called as independent variables or input variables, or we called as features, or we sometimes call as predictors. These are the different names given to the input variables. In different books, you will find it has been it has been named differently. Okay. So here in this case, we are calling it as an independent variable because this is the variable on which this particular output variable is dependent on. Okay. Now, similarly, just the small example what we have taken, right, X and Y. So here also we have a data in which I identified the input variable which I want to use. As I'm talking about simple linear regression, I will only select one particular variable. Let's suppose I've selected this one particular variable, and based on this particular variable, I want to predict this particular variable, which is my Y, or called as dependent variable. So I will take some historical data. This historical data will help me to come up with the equation. So I'm feeding some examples, some past historical data, like when the engine size was 2, the CO2 emission was 196. When engine size was 2.4, my CO2 emission is 221. Let's suppose I've given you this data. Can you easily identify the equation? It would be difficult. The earlier example was very simple and trivial, so you have easily we could able to come up with an equation. But in this case, it's not that easy. Okay, humanly, it would be difficult to identify the relationship between engine size and the CO2 emission. So now I will use this historical data. I will apply this regression model on top of it to come up with an equation. And once I get the equation, now I can predict the CO2 emission based on this engine size. Now in the real scenario, you will get the data like this. Okay. Now what you can do is first you go and do the correlation analysis. Find out the correlation of engine size with CO2 emission. Find out the correlation between cylinders and CO2 emission. Find out the correlation between fuel consumption and the CO2 emission. And based on that, identify which of the variable is strongly correlated among all these three. Let's suppose we have come up with this particular variable because this is the relationship between engine size and the CO2 emission is much more stronger than these two variables. Now, once you identified which variable is significant, which variable is impacting a lot the CO2 emission, you consider that particular variable and then go with a simple linear regression to come up with that kind of model. And that equation itself is known as model. That is known as predictive model. That predictive model, and now this regression is giving you an equation. There are multiple other machine learning algorithms which will give you a model in different other ways, not just equation. It will give you the model in different other formats, which we will discuss later. So as in our real life, internally, unconsciously, we'll try to find out the relationship between the input variable and the output variable. And that's how, we make the decision on any value given to us for the input variable. And based on that, we will calculate the output variable. So for example, businesses, how they come up with a price, okay, the price value of a particular product. If they are not using any data, if they are not using any predictive algorithm, it is feed it into their minds. Okay, they might have seen that if they are increasing the price by one unit, okay, then what would be the impact on their sales? Then accordingly, they are reducing or they are increasing the price. And they know that if they increase the price by $10 or 10 rupees, how much would be the impact on the sales? So that is happening in their minds unconsciously. Okay. And that based on that, they are making the decisions. Now we are venturing into an era where all these decisions are driven by the data. Okay. So we call it as a data driven decisions. So here we can apply all these techniques like correlation, regression, and try to understand which of the variables would impact my sales, identify those variables, and then build this regression model, to predict how those input variables would impact my output variable. Okay. So in the simple linear regression, I'm predicting this CO2 emission based on this engine size. Okay, for all the different cars. Okay, so I just need engine size. If you give me the engine size, I can able to predict the CO2 emission. So here the independent variable is your engine size and the dependent variable is your CO2 emission. In the multiple linear regression, instead of having only one single input variable, I can have multiple input variables. So for example, in this sales, now this sales, that it would be get impacted, let's suppose by price and also by discount. Generally, we have seen, right? If we reduce the price, definitely the sales would increase. And even if we are giving discount on a particular product, the sales would increase. So here, these two are the important features or important variables which would impact my sales. Now, here I will go with a multiple linear regression where I will consider more than one single variable as my input variable, and based on that, I will try to predict my output variable. So in this case, let's suppose I want to predict CO2 emission based on the engine size as well as the cylinders of the cars. So here my independent variable would be two, engine size and cylinder. I can have many more. Okay, there is no restriction. You can have 20, 30 variables also. And it could be continuous or it could be category. Now the dependent variable always needs to be one. So you need to identify what exactly you want to predict. That's something you have to identify from the data. And this is not an easy task, guys. Okay, sometimes what will happen is your business will give you the entire data to you and say that, okay, see that what you can do around advanced analytics. What kind of predictive models can you build by looking at this data? If you have a business understanding, then you can think about the output variable or the target variable, which you can use to build any kind of a predictive model. So if I get access to my CRM database, in the CRM database, I will get all the details related to my customer transactions. Okay. So now I can go through that data and see that which kind of customers are making what kind of transactions. So I can think of developing a predictive model which would predict how much transaction a particular customer may do. Okay, um, given that he's belong to this particular region or with this and he's male or female, or given that his income is this much. So all that would be my input variables. So now if I can able to train the model, now tomorrow if any new customer is coming, I much more in advance, I can predict, how much revenue I can generate from this particular customer. And then I can target those customers better. So in some of the scenarios, a proper define business problem will not be defined to you and given to you. Sometimes you have to come up with the business problem by looking at the data. That you can only come up if you have a good domain understanding and the data understanding. Okay. Now, how does this linear regression work? Now, I'm talking about simple linear regression where I have one output variable and one input variable. So this is my X and this is my Y. Now, firstly, I will go and plot this data. Okay, I will go and plot a scatter plot. Now, this is how my scatter plot would look like. Okay, if I ask you, just by looking at this scatter plot, can you tell me the relationship between Y and X? I'm not saying define the equation. I'm just tell me how they are related to each other.
As X is increasing, Y is also
Right.
increasing.
So we can say that Y
Directly
and X,
proportional.
they are directly proportional. So we see that as we are moving towards right, the points are moving towards upward. Okay, so that means as X is increasing, my Y is also increasing. So there is a upward relationship, or we can say that there is a direct relationship. Now, to train a model, okay, I need to come up with a line, okay, a straight line, which would fit well onto this particular data. Now, let's suppose I'll come up with this particular line like this, or this line. Do you think it is fitting well? No, it's not fitting well. If I come up with a line like this, and that seems to be a good line, based on this particular line, I can predict not 100% accurately, but at least, 80 to 90% I can yeah, accurately, I can predict Y based on X. Now, I have to choose now which line is a good line, which is fitting well to my data, current data. Now, a line which fits well onto this particular data is known as line of good fit. Now, this regression algorithm will help us to, to find the line of good fit. Now, how does that work? Okay, so this is the straight line. Now it has to pass from the center. Why it has to pass from the center? Because I don't want a line like this. Okay, if the line is going like this, if you see most of the points are below this particular line, and my error would be mostly negative. If I take this particular line, okay, so whatever predictions I will do, those predictions would be lower than the actual values. And all my errors would be positive. Okay, positive is nothing but actual minus predicted. Okay, it's the difference between the actual and the predicted values. So I want a line which pass through the center, and so that my overall errors, if I add, it should come out to be as 0. There would be an equal positive errors and equal negative errors. That generally doesn't happen, but this whole algorithm will try to come up with an line which fits well and which pass through from the center. Okay, through which, by which, we can able to, and that we call as a line of good fit because it is not biased now. If it is like I'm getting all negative errors, if I'm getting all positive errors, so that means my model is a biased model. Okay, and it is kind of getting influenced by certain observations because of which I'm getting all negative errors or all positive errors. So I have to make sure my line is passing well between the points and it is not biased. Okay, that's something we'll see step by step how it will identify that. Okay, now once we get this particular line, now at any x value, I can able to find out the y value either through this visual representation or else by that equation. Okay, y equal to beta 0 plus beta 1x, where beta 0 is this particular slope and sorry, beta 1 is this particular slope, and beta 0 is this intercept. Okay. Now the equation of this line is given like this. Again, in different books, it is represented in a different way. Somewhere it is shown as beta, somewhere it is shown as theta. Okay, now here it is shown as theta. Here, the whatever values we are predicting of from this particular line is denoted by y hat. The actual values are denoted by y. These are actual, these are predicted. And these predictions you can make by this particular equation, which is denoted by theta 0 plus theta 1 x1. It is x, sorry. Okay. So this is x. For any x values, sorry, it is x1 only, and they have denoted it as x1. Okay. So this is x1. Okay, so which is engine size. Now, based on this engine size, I can able to predict my emission of that particular vehicle. Now, to find out the error is nothing but your actual minus predictions, which is y minus y hat, or somewhere it is y hat minus y I. So basically, it is nothing but the difference between your actuals and the predictions. Okay, so that is your error. All right, so yeah, so how to find the best fit? Okay, that's something we will understand. Okay, so basically, if I ask you which line you will consider as the best fit, a very layman question if I ask you. There are multiple lines. Which line you will fit, you will choose. So your answer would be a line which is giving me the minimum errors. So all these points which are there in my data set, all those would be my actual values, like y1, y2, y3, y4, y5. And with these, each of the lines, I will make the predictions. For example, y1 hat, y2 hat. So these are all my individual regression lines. Okay. And from each of these lines, every line will have a different equation, right? Because the beta 0 and beta 1 would be different for each of the lines, right? So I will consider each of those equations, and for every data point, and there would be a x also here, x1, x2, x3. At this particular x1, I will calculate the y11 hat, okay, y12 hat, y13 hat. So like that, I will calculate for every regression line. Then finally, I will go and find out the difference between the actual and the predictions which are coming out from each of these lines. And then I will find out the difference between the predictions and the actuals to calculate the error. So I'll find out the error one, which would be the overall sum of the errors for all the observations, okay, which is y1 hat minus y hat. Okay. So like that, I'll find out the errors for all the lines. E1, E2, E3, E4. Those are my total errors coming out from each of these equations. Now, whichever model is giving me the least errors, a minimum error, I will choose that particular line. So if we have to choose from all these lines, I'm sure that this particular line will give me the minimum error when compared to all other lines. Now that line will become my best fit line, okay, which is fitting well onto my data. Okay, so this is my error. So this is how I will calculate the error, actual minus predictions. So visually how we find out the error is, let's suppose this is my actual value, but I predicted this. So actually it is 250, but my equation is predicting as 340. So what is the error? It is 250 minus 340, so which is minus 90. Now this is my error, which is given by this red line. This much is my error. Now, what this algorithm will do is it will try to minimize that particular error when it is getting trained on the historical data. So it will try to fit on the historical data. Now, this particular algorithm will try to optimize. So initially, let's suppose it has come up with this particular line. It will try to optimize the way the program is written. It will try to optimize, and it will try to come up with a particular point at which my error is minimum. Now, this particular error is known as, in mathematical language, it is called as cost function. Now, programmatically, the way the regression model is written as, so this cost function, it will try to minimize over multiple iterations. So we'll see that, how it is done. And once it reached to a point where the cost function is minimum, it will stop there. The program will stop there. And at whatever beta values like slope or the intercept, it has reached to a minimum point. That would be my final parameters which I can use for my equation. Okay. Now, this is also, and now what is that cost function is? This is my cost function, which is denoted as mean squared errors. Now, why we are squaring the errors? We have seen that a line which passes from the middle is considered as a better model. But we will not get a clear picture of the errors because we will get positive errors, we will get negative error. If we sum it up, they will get cancelled and we may come up at a point if it is passing exactly from the middle, the sum of the error may come out to be zero. Now this could be misleading. It says that there is no error at all in this particular line. But is it true? It's not, right? There are errors. There are positive errors, there are negative errors. But overall, if we sum those errors, it may mislead us saying that there are zero errors. This particular line is giving me the zero errors. So that's the reason instead of summing all the errors, we go and use this particular matrix as a cost function, which is mean squared error. So we will first, whatever errors are coming, we will convert that into positive. Either we can take absolute values or else we can square those values. And typically we have seen in statistics, instead of going with absolute, we generally prefer doing square, right? That we have seen in the variance classes, right? In the variance also, the deviations, we are squaring it off. So this is my squared deviations or the errors, and then I'm taking the average of those errors. So on an average, this is the error. Okay, this is the squared error which we are getting out of this particular equation. Now this mean squared error which we will use as a cost function, and this particular algorithm will try to minimize that particular cost function by changing the beta 0 or this theta 0 or theta 1 coefficients. These coefficient values, it will try to find it out multiple times, and also it will check the cost function and it will stop at a point where the cost function is minimum. Now your question would be how it is done, how it will identify whether that cost function reached to the minimal point or not. So for that, we have another program which will run behind the scenes known as gradient descent. See, there are two ways of finding out these coefficients, optimal values of these coefficients, which will give me the good fit. One is the statistical way of doing it. If you refer to any statistical book, you will find one statistical way of calculating these coefficients. But those are not much efficient when it comes to programming. And we need a much more effective way of identifying these optimal values. So that's where the mathematicians, they have come up with this gradient descent algorithm, which is a optimization algorithm. It's an optimization algo, which we will use to find out this optimal coefficient values like theta 0 and theta 1, where the objective function of this optimization algorithm is to minimize the cost function. Okay. So now this particular program, what it will do is, it's like this. Okay. Uh, for example, I have, what do you say? Let's suppose there is a parameter X, which is in my control, and there is a Y. Now, to define this Y, I have these two parameters, beta 0 and beta 1. Okay. Now, based on this, I am calculating the Y, which is my Y prediction, and then I'm finding out the error. Okay, which is the difference between my actual Y and the predicted Y. Now, this whole process is I'll come up with some values of beta 0 and beta 1. Let's suppose I take it as 1 and beta 1 as 2. At this particular x1, I'll calculate the y, and then based on that, I'll calculate the error. Let's suppose the error is coming out to be 20 overall. Then I will change this beta 0 to 1.5 and this to 2.4. Then I will see what is the error. Now, let's suppose it has come out to be 14. Now I'll change the beta values like 0.7 and this as 3.5. Now it has drastically reduced and the overall error is coming out to be 7. Now this program will check, is there any further chance of further reducing the error? If not, then it will stop it here. Now this is the called as global minimum. Global minima means at after this point, there is no possibility of further reducing the error. Now these are my optimal beta 0 and the beta 1 values, which I can use to calculate to predict the y variable or the dependent variable. Because this particular parameters or coefficients are giving me the least error or where the cost function is minimum. Now this point is known as global min. Now this is the overall mechanism of this particular algorithm known as gradient descent. Okay, we will understand more about gradient descent. So now if it is a simple linear regression problem, so theta 1 can be easily calculated by this particular formula. This is a statistical formula. Okay. And if you have calculated theta 1, now theta 0 can be calculated by this particular formula. You just require the mean of output variable and the mean of input variable, and then this theta 1 value. So if theta 1 value you substitute in this equation, you can able to calculate the theta 0. So it is okay for the simple linear regression. We can go ahead and use this particular formula directly. But when it is comes to multiple linear regression, where we are talking about multiple coefficients, there the statistical equations generally would not work. Okay, in that case, we go and use this gradient descent to find out the optimal values. But the in Python, whatever functions are written, backend it is the gradient descent only. They are not using statistical formula like this, to calculate the coefficient values. And it seems that both the gradient descent and the statistical methods ultimately eventually give the same values. But computationally, the gradient descent is much more faster when it comes to multiple linear regression when compared to those statistical methods. Okay. Now, this whole method statistically, it is called as ordinary least squared method. If you remember, yesterday we have used in Python, we have used a function in which there was it was mentioned as OLS. OLS is nothing but ordinary least squared. Ordinary least squared, as we have seen, right? So these are all squared errors which we are calculating here. So least squared means I'm finding out the parameters which are giving me the least squared errors. So that method is known as ordinary least squared. Okay. So if somebody asks you which technique or which method generally regression uses, to come up with a line of good fit, you have to say OLS method. OLS method means it will try to come up with the parameter values which are giving you the least squared errors. Okay, so that is known as ordinary least. Okay, so like this, I will first calculate the theta 1 value. Once I know the theta 1 value, I'll go and substitute that in this particular equation. I'll find out the theta 0 value. Now once we have theta 0 and theta 1 value, I can able to predict the y variable if I have the input variable given. Okay, I'll take a pause. Any questions till now? Is it clear? So gradient descent we will discuss. Okay, that's the main crux of the entire model, and you will find that this particular gradient descent even we will use in neural networks. Okay, so this is the very good invention happened in this data science space. Earlier, they were using statistical method in the programs. There were a lot of tools. They were using all this statistical method, but now these mathematics based algorithms cons- uh, came out to be even much more efficient than these statistical methods, because these mathematical equations can help you to compute things much more faster when compared to the statistical techniques. So that's the reason machine learning algorithms, these are mostly they are mathematical based equations which we will use to come up with a predictive model. Now there are certain pros and cons for this linear regression. It is very fast. If it is simple linear regression, so basically it has to compute these two parameters. So which is relatively very, very fast. Okay. Within fraction of seconds in Python, it will calculate your theta values and your model is ready. Here, there is no parameter tuning, which we will discuss, because here the parameters are nothing but beta 0 and beta 1, which this algorithm itself it is finding tuning and finding out the optimal values. So no need of again going and doing some kind of tuning. But in other machine learning algorithms, you will see that there would be certain parameters which you have to tune yourself to make the model better. To make uh, to increase the accuracy of the model. Now, another major advantage of this linear regression is it is easy to understand and highly interpretable. So what we mean by this? See, now if you go and tell to the business, now I have a model, predictive model, go and give me the price values, I will tell you what is sales. Okay. Say, man, how you are predicting? Did you get a superpower? Or how you are predicting this sales if I'm giving you the price? You say that I have a model. So he will say, explain me the model, how the model is predicting. Tell me. Okay. Now you would be able to explain these linear regression model. And people can understand this model and can validate and can interpret these models, linear regression. When we move further, we will find certain advanced machine learning algorithms which cannot be interpretable. You cannot able to explain, what is happening behind the scenes. Though the accuracy would be very high, but those would be non-reliable and not trustworthy, okay, in terms of when prediction comes and you won't be able to understand how it is coming. So we need to decide where to use those algorithms, where to use these kind of algorithms. If business would be interested to know how the predictions are happening, then you should go with the simpler models, which are easy to understand and which are highly interpretable. So model interpretability sometimes would be a important factor to look at, when you're building a predictive model. Now, once the model is ready, now you have to evaluate. So model training is one part, then comes the evaluation. We have seen that, okay, there are either you can use the same measure, MSE, to calculate the errors. But once the model is trained, okay, and you are evaluating, if you use this MSE score, again, this cannot be interpreted by the business. Why? Because here you are squaring the errors. Okay. So here the errors, let's suppose here it's the errors are in tens, right? So for example, now you have come up with prediction as 20, once again, 2010, let's suppose. Let's make it easy. Let's suppose my prediction value is 2011. So what is the difference? Difference is of 10. If I take the square of it, it will show you as 100. When you give it to the business saying that overall the error square is equal to 100, they cannot interpret it nicely. What you can do is if you take the square root of these all errors, now that would come back to the same unit. Now, if you say that there is a plus minus of 10 units, then it make more sense and the business will understand. So for that, we will use RMSE as root mean squared error. This is one of the evaluation matrix we use, when we are predicting any continuous variable. Okay. Or else there are many other. This is known as MAE, which is known as mean absolute error. Here the errors, we are taking the absolute values. So why we are taking absolute values? Because we want to convert the negative values to positive. And if we don't convert, then there would be positive error, there would be negative error. If we sum it up, there is a chance that we may get zero error, which will be misleading. Okay. So take away from this slide, the evaluation metric or evaluation measure which we will use to test our model accuracy here in this case is RMSE, which is most popularly used RMSE, okay, which is root mean squared error. So if I have to give you the formula of RMSE, it would be square root of this. That's all, called as RMSE. So this would be my evaluation matrix, which I will use for my prediction. Now, before getting into all these things, one important thing which I missed to explain is the overall procedure for training a model. Now, let's suppose you have a data. Now, in this particular kind of data, let's suppose we have Y and we have X. All this data is coming out from my database. All these are historical data. Okay. Now, the process of training a predictive model is that I will split this data into two parts. Now, again, this is not the entire data which is sitting in my database. What I did is I did a random sampling. Okay. And I took one sample of data. How big the sample of data should be, it depends on the kind of problem you're solving and the kind of algorithm you are using. So here in this case, let's suppose I picked up some 200 observations from this particular database. Now this would become my data set for my model training. Now the second step is definitely we have to do data processing. We have to check the quality of the data. All this thing we have to do. Once the data seems to be good, now what I will do is I'll split the data. How I will split? I may split by 70%, 30%, or I'll take 80%, 20%. Okay, so any value between 70% to 80% is a good amount of data which you should consider for your model training. Now, this is known as training data set. Okay, and the remaining data is called as test data. So let's suppose this is my 100% data. I took 70% of this data as my training data set. Okay, it would be somewhere between 70 to 80%, and this would be somewhere between 30 to 20%. So majority of the data points I will consider as my training data set, and the remaining observations I will consider as my test data set. Now on this training data set, I will go and train my model. So we call as model training. Now in this particular scenario of simple linear regression, I'll take this training data set, and once I'm training my model, I will able to get this beta values. Only on this particular training data set, it will go and try to find out the optimal beta 0 and beta 1 values. Okay. Now in this training data set, again, I will have y and x. In this also, I will have y and x. Now here I will feed all y and x to the model. Just now, the way we have tried to identify that equation, right, between y and x, similar way, this linear regression model will try to algorithm will try to come up with the optimal beta 0 and beta 1. Once this beta 0 and beta 1 is identified through this model training process, now I will have a equation y equal to beta 0 plus beta 1 x. Now this will be used on the test data set. Here in this test data set, I will pass only the x variable to it, and then I will calculate the y, which is y hat. Now, based on this, I will go and test my model. So this is known as model testing. Okay. And here we have discussed about RMSE. The RMSE is a score by which I will test this model, how good my model is on my test data. And here, while training, I will try to find out at this particular beta 0 and beta 1, how this model is performing. Okay. And what is my RMSE on my training data set. So definitely it will do its best, to find out the best optimal values, which is giving you the least error. So here it will try to come up with the best RMS. Now, while testing, I have to see whether on my test data set, because this I have not passed to the algorithm. This is completely unseen data. It is something like this. Okay, I will ask you to learn, right? And I will say that there would be a test. So I will give you, let's suppose, 20 problems along with the solution. And based on that, you will do your learning. Now, this model training is also known as learning process. So that's the reason we call as machine learning algorithm. Here, the algorithm is learning the pattern. Once it has learned, it will acquire the knowledge. Now, this is the knowledge. These parameters are nothing but the knowledge in mathematical terms. Now, once the knowledge it has gained, now that knowledge we will use for testing on the test data. So test data is nothing but I'm giving you a very different unseen question, which I haven't given you before. If you have learned the concepts better, you could able to solve those problems accurately. If this model has generalized the relationship between the input variable and the output variable, it should able to give me the accurate prediction on the test data. How I will compare? I will compare with this RMSE. What is the RMSE I'm getting on this training data set, and what RMSE I'm getting on the test data set? If RMSE is higher, if the accuracy is higher on my training data set and the accuracy is bad on my test data set, now that is known as overfitting problem. I cannot use that model for prediction. Though it has given me a good accuracy, high accuracy on the training data set, but it failed on the test data. So that means it's overfitted model. Okay, we will talk about a lot of other terms like if it's an overfitted model, how we can able to uh, reduce that overfitting problem. We will understand later. If my model is not giving better result or better accuracy on my training data set, now that is known as underfitting problem. And there are ways, by which we can solve this particular problem. If we do not have a overfitting problem, if we do not have an underfitting problem, that means my model is good enough. I can go and deploy it in the production. Now, this is the whole process for model training. You take the data, take the sample, split that into training and test, train your model on your training data set. And once the model is trained, you go and test it on your test data set. Firstly, after training, you have to check if your model is giving better accuracy or not. If it is not giving, then it is a underfitting problem. If it is giving, you move further and you go and test the model. But if your model fail here, then that is a overfitting problem. It is if it is giving the good accuracy even on the test data set, that means your model is a good model. It's a robust model which is giving you good accuracy on your training as well as on the test data set. Now you can go and deploy that model. Okay, so this is my whole model training process. So I'll take a pause. Let me know if you have any questions. And this process, don't worry, we will repeat whenever we are talking about any machine learning algorithm. For every machine learning algorithm, it is the same process. The only part is like here the algorithm would change. Here now we are using simple linear regression model algorithm. Tomorrow we may use multiple linear regression. After that, we may use any other machine learning algorithm like decision trees or random forest or support vector machines. The process will be the same. The only part is the algorithm may change here. That's all. Okay, so this we have discussed. Yeah. So here the training accuracy. High training accuracy isn't necessarily a good thing. Okay, so in the training data set, you may get a high accuracy. You should not jump and be happy that, okay, I got a very good accuracy on a training. First, you have to go and test it on your test data set. If the result is poor, then it means it's an overfitting model. So overfit model is the model is overly trained to the data set. That's the reason you are getting high accuracy on your training data set, which may capture noise and produce a non-generalized model. Non-generalized model is a model which is performing better on your training data set, but not on your test data set. See, now you can relate it to your our human lives. And every algorithm I'll try to relate to the human life. For example, I've given you 20 problems along with the solution and I have asked you to learn. Now, what you have done is, let's suppose you've been smart, okay, and what you did is you have by-hearted those problems. Now, let's suppose I came back to you and said that, and I will ask you, have you learned these 20 questions? You'll say, yes, sir, you ask any question out of this 20, I will solve it. But what you did is, you have not understood the concept. You by-hearted those problems. And you have by-hearted so well that I gave you two problems and you have done it 100% accurately. You have done the way that solution has been given to you. So here, your accuracy on that particular data, those 20 questions, is very high. Okay. But now I'll say, okay, fine, that's good. Okay, you're doing extreme. Now I'll do one thing. I'll give you altogether a new question now. If I give you a new question, now you will fail drastically because you don't know what concept to use because that is altogether a different question. So when you mug it up, when you don't understand the concept, if you don't generalize the problem, your accuracy would be very high on the data which is given to you, but you may fail drastically on the new data which you haven't seen before. The same way for these models. Models sometimes it may learn too much, okay, from the data that on the training data and even the algorithm which is running behind the scenes, right, the gradient descent, it will optimize so well that it may able to reduce the cost function till zero and it will give you the optimal beta values. So that means on the training data set, it has overfitted. It has learned all the possible patterns and relationship from that particular data. But when you try it on your test data, it would fail. So in that case, it's an overfitted model. I will explain you if you get into this kind of a scenario when you're training the model, how to fix it. Okay, that we will discuss later. So because that is a very generic concept and that would be applicable for any machine learning model training problem. Okay. One other problem is out of sample accuracy. Out of sample is, let's suppose I given you altogether different questions to learn, and I'm giving you altogether different question, for testing. You may say that this is out of syllabus. You haven't given me any question related to this. How can you test me on this? So you have to be very specific when you are training the model. You have to make sure that all the similar observations are there between in the training as well as on the test. That's something you cannot check observation by observation. You have to look at a holistic level. If you remember, we discussed about the data, right? The environment, the characteristics, the behavior, and all those things. All those things need to be keep in mind. Okay, you cannot collect the data of a particular environment and train your model and then apply that model on the data which is collected altogether in a separate environment. Okay, so here the data is not similar in your training and test. So that is known as out of sample. So out of sample can be improved if you make sure that the data is similar between the training data set and the test data set. Okay. So all these checks and balances measures which needs to be considered while training the model, we will keep discussing that. I don't want to give you all the pointers in the beginning only because it may confuse. Every time whenever we are discussing a new algorithm, we will bring one new concept, okay, which we will go through to make sure my model is accurate. Okay. So now this is my training data. I'm given it to the algorithm. The model is trained. That model I'm passing to that particular model. I'm passing this test data and I'm getting the predictions. And these are the actual values. And I will compare these actual values to see how my model is giving me the result on my test data. So this test data is unseen data. If it has worked well on this test data, now tomorrow you give any kind of a data to this particular model, it should able to give me the better results. Okay. Okay, there are various approaches to this. You take one data set and then divide it into two parts, training and test. So here the observations will not uh, here there would be a different portion of the test and the training data set. So there wouldn't be any kind of overlap. Okay. So here you may get a high training accuracy and the low out of sample accuracy. Okay. Because here the data is completely different. So there could be some scenarios that the observations could be relatively similar. There could be certain observations which could be completely different. Okay. So you have to make sure that a data is kind of it should be mutually exclusive, but the data should be the similar representation you need to have in the training as well as in the test. So, for example, I'll give you an example. Uh, let's suppose a machine failure. Okay, if I'm training my data on a certain kind of failures, so it will learn those patterns only, right? If I go and try to predict a machine failure in altogether different pattern, I haven't trained my model on the voltage specific failures. So if there is any voltage fluctuation happening, my model would not able to predict those kind of failures. Okay. So in that way, my model will fail on my model will not able to predict those kind of failures on my new data set. So I have to be very clear that all the different kinds of possible scenarios are covered in my training data set and to some extent in my test data set. Okay. If I do that, then that particular problem will be addressed. Now, for the overfitting problem, how can we solve that? So there we will talk about this k-fold cross validation. So by now, for now, I'll just skip it. We will come it later. So I don't want to bombard with lot of different topics. So this we will cover later. Okay. So this is what are the training accuracies, evaluation metrics I spoke about, mean absolute error or mean squared error or RMSE. So primarily we go with an RMSE because this is something we can explain better to our stakeholders. Because these errors would be on the same unit, same scale. So if I say this model is good enough, it is giving roughly around plus minus 10. So if the CO2 emission, if the model is predicting with plus minus 10 error, okay, then the business can decide whether this model is good enough to be used or not. Okay, so the RMSC will give that kind of value of errors on the same scale. So these are the formula. Okay, so I'll stop it here. Continuation to this particular class, this particular topic, we will talk about gradient descent. That is something, okay, that's a core part of this algorithm, which we'll discuss tomorrow. Today, I given you a general idea about what correlation is and how that correlation can help us in terms of identifying the important variables. That is the first step. Whenever the data is given to us, we first go and do some kind of analysis on top of it to understand the quality of the data. We'll do all that descriptive analytics, and then we will do some correlation analysis to understand which of the variables are strongly correlated and which of the variables we can use to predict our output variable. Once that is done, once that is done, I will move forward and I will do the predictive analytics where I can choose any particular machine learning algorithm. I'll consider the training data set. I'll apply that machine learning algorithm. I will train the model and then I will test that model. First, in the training, I have to evaluate how that model has trained, how much the model can able to predict my output variable to what level. So if it is doing a good job on my training data set, then I will go and test it on my test data set. And then accordingly, I can decide whether it is an overfitted model or it is a good model, and then I can go and deploy that model. So today we discussed about a linear regression. What is linear regression is all about? What are the different types of linear regression, simple linear regression, multiple linear regression. And then we discussed about simple linear regression in much more detail. You know, how that through simple linear regression, we can come up with that linear equation, okay, and which will use it as a predictive model, which will help us in predictions. Okay, so what is the time now? Okay. Yeah. So time check. Okay. So I think we are up with the time. So this is what we have discussed. Tomorrow we will discuss about gradient descent and some other concepts like cross validation and all. Okay. So we'll go relatively slow and the same topics I will repeat again and again. But whatever we have discussed so far, okay, so please revise that, those statistics and everything, because that is very important. And I will bring that statistics here also in this linear regression, which would be important for us, to interpret the model, to understand the model. So there is a lot of statistics which will come out of the model, okay, which we need to understand. So for that, you need to have a good understanding about all those statistical tests, which we have discussed. Okay, so we are right on time, so I will stop here. If you have any questions, we can discuss. Otherwise, we'll wrap up. All right, guys. Then thank you so much. We'll connect tomorrow. Thank you. Bye bye.